Hi, this is Dane Quinn, and today I'd like to talk about Laplace transforms. So a Laplace transform is an operation that converts some function of time, say f of t, into a new function with a different independent variable, namely f of s. Right? So the Laplace transform is defined here as an integral from 0 to infinity of that original function of time times e to the minus st dt. And again, so what we end up with is some new function of this Laplace variable, which we refer to as s. Right, so, for example, if we take f of t to simply be a constant, maybe 1, and it's defined for t greater than or equal to 0, so this integral makes sense, then when I evaluate the Laplace transform of 1, right, I basically just put 1 in here for f of t. Right? So I get the integral from 0 to infinity of 1 times e to the minus st dt. So I can do this integral, right, and it ends up as minus 1 over s e to the minus st evaluated at the endpoints. Right? So t is equal to 0 to t is equal to infinity. Right? So when I evaluate this, e to the minus s times infinity is 0. Right? And then subtract off the argument here evaluated at t equals 0. Right? So we end up with just simply 1 over s. So when I take the Laplace transform of 1, I get 1 over s. And if I had 1 over s and I wanted to go back, then I would take the inverse transform and I'd get back to 1. Right? So again, that's a common way of looking at Laplace transforms, both forward, right? So starting with f of t and taking the Laplace transform and calculating f of s, but then also doing the inverse transform, right? So starting with f of s, and the inverse transform is often abbreviated as L to the minus 1 power, or L inverse, and getting back f of t. So here's some common functions, right? This, again, this function 1, the Laplace transform of t, e to the minus sigma times t, right? So here sigma is a constant. We can take the Laplace transform of sine and cosine omega t, right? And we get these forms. And then this damped harmonic response, right, gives me a Laplace transform of here for sine and this for cosine. Right? So this is just a basic Laplace transform table. Now, the Laplace transform also has some very nice properties. Right? In particular, it's a linear operator, which means that if I take the Laplace transform of some constant, c1 times a function, plus another constant, c2, times a different function, then I end up having the Laplace transform, well, c1 times the Laplace transform of this function, f1 of t, plus c2 times the Laplace transform of f2. Right? So this is just a linear operator. And oftentimes we abbreviate this as some Laplace transform function. Right? So this might be f1. We might call this f2 of s. So at the end of this, we get c1, f of s, f1 of s, and c2 times f2 of s. Right? So again, if I have two functions added together, take the Laplace transform, right? It's basically the Laplace transform of the two functions independently. Now, the other really nice property of Laplace transforms is how they operate on derivatives. Right? So in particular, if I have the Laplace transform of df dt, right, which again is some function of time, using this definition, we get the integral from 0 to infinity, df dt, e to the minus s times t dt. But we can evaluate this, right? So in particular, if we use integration by parts, right? So let's define our integration by parts variables as u is e to the minus st, which means that du is minus s e to the minus st dt. dv would be df dt times dt, which means that v is simply f. So now, using integration by parts, this becomes vu, right, which is f of t times e to the minus st, evaluated at the limits, 0 to infinity, minus, and then v du, its integral, 0 to infinity, f of t, and then minus s e to the minus st dt, right? So again, integration by parts. Well, let's go and evaluate this. Again, evaluating t equals infinity, this goes to 0, and then this becomes minus f of 0. And then looking here, well, s is not the integration constant, right? So it can actually factor out, and then we have two negative signs, right? So we end up with s times the integral from 0 to infinity, f of t, e to the minus st dt, right? But that's simply the Laplace transform of f, right? So when I take a derivative, when I take the Laplace transform of a derivative, I end up with s times the Laplace transform of the original function minus f of 0. So this ends up being really nice for differential equations because derivatives are transformed into just the function f of s itself. Again, possibly multiplied by s or some higher powers. So Laplace transforms end up converting differential equations into algebraic equations, right? So again, I have this property that we just looked at. If we do the same thing for the second derivative, then the Laplace transform of x double dot ends up being s squared times x. Again, x of s is the Laplace transform of the original variable. And then we have some initial condition dependence here. So this is going to be the initial velocity. Right, so if I think about kind of like a flow chart, we start off with an ordinary differential equation, and if I take the Laplace transform of the entire equation, I end up with an algebraic equation in terms of the Laplace transform variable. Right, and ultimately what I want to do is solve this ODE and find x of t. Well, when I take the Laplace transform, again, solving this is relatively straightforward because it's algebraic. Right? So I can just solve for x of s from this algebraic equation. And of course, that is the Laplace transform of x of t. And so once I know that, I can take the inverse Laplace transform and recover the original solution. So this is nice, right? Algebraic equations are typically easier to solve than differential equations. Right? But we do have to take the inverse Laplace transform in order to recover the original solution in time. Right? Yeah. So the inverse Laplace transform, which again is kind of abbreviated as L inverse, is used to recover my time solution x of t. Right, so let me actually apply this to this simple ordinary differential equation, basically a spring mass system. Right, so I'll start with mx double dot plus bx dot plus kx equals some forcing f of t. Right, and then we'll have the initial position as x naught, and we'll have the initial velocity as x naught dot. Right, so essentially, I'm going to take this entire system and take the Laplace transform of this. So again, the Laplace transform is linear, right? So it's simply the Laplace transform of all these individual terms, right? So that becomes m times the Laplace transform of x double dot. Well, that's up here. S squared x of s minus s times x of 0 minus x dot of 0 plus b times x dot, well, it's Laplace transform, right? So that's s times x of s minus x 0. Then we just have kx equals the Laplace transform of f of t, which we'll define as f of s. So notice that this is now an algebraic equation in terms of x of s, right? So we can solve. X of s is, well, let's take everything that doesn't depend on x of s and put it on the right-hand side, right? So we get f of s already there. And then we have all these initial condition terms. So in particular, the stuff that depends on x 0 is m times s plus b times x 0 plus m x dot of 0. And again, those values are just given here in terms of the initial conditions. And of course, that's divided by now ms squared, right here, plus b times s there, plus k. So once we have this, x of t, the time solution, is determined from the inverse Laplace transform of this function. Right. So let's go and look at that in a little more detail. Right here again, I have the response, the Laplace transform. Right, so this first term comes from the forcing, and this second piece comes from the initial conditions. Right, so in particular, if I look at the relationship between the forcing and the response, right, x of s, I find that x of s is simply this piece in square brackets, right? So it's 1 divided by ms squared plus b times s plus k times f of s. Notice that this doesn't depend, this term in the square brackets doesn't depend on actually what the forcing is, right? The forcing can be anything, and this term tells us how to relate the Laplace transform of the forcing to the Laplace transform of the response, right? So that's actually an important property of the system. And oftentimes it's written as its own term, right? So we'll call this h of s. Essentially, it's the ratio of the output, right, or the response to the input, f of t. Right? Again, in this system, it ends up being 1 divided by ms squared plus bs plus k. Right? So this is known as the transfer function. It relates the input and the output of the response. Right, so in general, in the Laplace domain, right? Sometimes also referred to as the S domain. The response, the output, is simply the transfer function times the input. And so again, we have the response, we have the transfer function, which is a property of the system, and then we have the input. This oftentimes gets represented sort of pictorially in the following form. We have the forcing coming into a block, which describes the transfer function or the system, and then that gives rise to the response. Right? So this is, again, sometimes known as a block diagram. And as we get more complicated systems, right, this becomes really useful, because you could have one component that has an input, but then feeds into a second component. That second component could have its own transfer function, right, which gives you the response. Right? So this idea of a block diagram is a really convenient way of sort of creating complicated systems from sort of their individual components. So let's look at a fairly simple example of a 2-degree of freedom system, right, and see how Laplace transforms can simplify the reduction of these multi-degree of freedom systems. Right. So again, here we have a disk. It's got a moment, mass m, radius r, and I'll define the counterclockwise angle as theta. That is then attached through an elastic cable with stiffness k to a block that is suspended with a damper. Here the pulley will be massless. X measures the displacement of the block. Right. So if I go through and I model this system with momentum balance, right, I end up with the following equations. Right. This comes from some of the moments about the center of mass of the disk is equal to the angular acceleration times I of the disk. Right. So this is angular momentum balance on the disk, and then this comes from linear momentum balance on the block. Maybe you want to pause the video here and actually go through, if you need a little extra practice modeling things, right? Maybe model this system, see if you can come up with these equations. But so if I have these, right, so I'll kind of start off with the equations and show how the transfer function can be developed between the response of the block and the applied moment. Right? In particular, so if I take the Laplace transform, and I'm going to assume 0 initial conditions here, because I'm only really interested in the relationship between the moment and the block response. Well, we'll get m1 r squared over 2, right? So we'll work on this first equation, right? Remember the Laplace transform of a second derivative will be s squared, right? Theta of s will be my Laplace transformed variable, right? So here, the Laplace transform of theta of t will be capital theta of s. The Laplace transform of x of t I'll refer to as, obviously, x of s. And then we have k times r. R times, well, this is going to be capital theta again, and then capital X, Laplace transform of x, equals, right, so here m of s. This is going to be the Laplace transform of this excitation. For this second equation, we'll get m2 s squared times x of s plus b s x of s minus k, r capital theta of s, minus x of s equals 0. Right, so these are my two equations after I've taken the Laplace transform. Right, and I can rewrite those into a fairly convenient form. Right, so let's pull together all of the terms that depend on theta and all the terms that depend on x in these equations. Right, so in particular we get m1 r squared over 2 s squared plus kr squared times theta of s minus k times r, right, again here, x of s equals m, and then my second equation becomes, in terms of x, m2 s squared, right, and here I'm assuming that m1 and m2 are the pulley and block masses, respectively, plus b times s plus k x of s, right? So I've just pulled together all the terms that depend on x, and then we have the theta term, kr theta of s is equal to 0. Right, so again, these two differential equations become algebraic equations. So if I'm interested in the response of the block given the input moment to the disk, then basically I just need to take these two algebraic equations and solve for x, right? And in particular x in terms of m. So when I do that, I end up with something that looks like x of s is equal to a transfer function times m of s, right? So again, response, transfer function, and input. And if I go through the algebra, right, and I'm not going to do that here, but I'll just give you the results, we find that h of s, the transfer function, ends up taking the following form. In the denominator, we have m1 r squared over 2 s squared plus kr squared times m2 s squared plus b times s plus k minus kr squared, and that is the denominator with the numerator equal to k times r. Right, so again, if you basically just solve this second equation maybe for theta, plug it in, solve for x, right, this is the result you get. So this transfer function describes the relationship between the applied moment on the disk, which is m of s, and the response of the block, which is described by x of t. Right, so again, these Laplace transforms typically turn differential equations into algebraic equations, right, that can be fairly easily manipulated. Right, so that's a pretty good introduction, I think, to Laplace transforms. And in the next lecture, we'll talk about how to really focus on the inverse Laplace transform. Right, so specifically how to take something like this, right, with some known input, and recover the response of the system. So that's it. Thank you very much.